is an example of power and efficiency. That's what we were introducing in class 9. So I figured I would do a problem with power and efficiency. So it's sort of like, I think of this as like an elevator problem, maybe. Something that you should note that we could, sometimes we could have power being positive or power being negative. So we might have an instance where we were being like sort of regenerative, like a generator for something, right? So just be on the lookout for that. The power supplied to the motor at this instance. So that's what really we want to find. I don't know if it actually says that in here. We have 50 kilogram block A is hoisted by pulley system and the motor. The motor has an efficiency of 80%. At this instant point P, right there, we can see that P has a velocity of 12 meters per second, which is increasing at a rate of 6 meters per second squared. Okay, so it's accelerating. Neglect the mass of the pulleys and cable, and it doesn't ask a question. I say, find the power supplied to the motor at this instance. We want the electrical supply that's coming into the motor. And remember that the motor is 80% efficient or inefficient. 20% inefficient, something like that. So this is a constrained motion problem first. So we want to set up a datum right to here. And I'm going to say this is going to be my SA. And then I'm going to go to P from right here, right? So this is SP right into right there. So what I end up saying is that SP plus 2 times SA is equal to the length. Therefore, the velocity of P plus 2 times the velocity of A is equal to 0, aka the velocity of A is equal to negative the velocity of P over 2, right there, right? And I can put in things, and we can put in a value here in a second. Velocity of P, the acceleration of P plus 2 times the acceleration of A is equal to 0, and of course, so the acceleration of A is equal to the 1/2 the velocity, the acceleration of P. So they gave us what the velocity was, right? So we could say this negative 6 meters per second. And there's 12 divided by 2. We could do that in our heads. And we also had this was 6 meters per second. So this is a negative 3 meters per second squared. Right, so obviously this thing is traveling upwards right here, right? So we might not even need to put that in there. I'll say that this is 6 meters per second upwards, and it is accelerating at 3 meters per second squared upwards. I don't like playing that sine game. It can burn you. Ice water. So let's find what the tension is, right? That's going to be good for things. So even though we've been using work and energy, this is power right in here. We know that power is force times velocity. We could even say that they're dotted against each other. So if we could figure out what the tension is, that that is maybe we would. Here's the rope, but we cut the rope right there so we can see what the force of the tension is going to be right here at that spot at P, and times the velocity. That's going to be the power that's going to be going through there. And we could do that at any spot right there, right? We could do just but let's take a look at it. Okay, so I'm going to do my Newton's second law onto this thing, and I think I'm going to do it for A. Right, I decided to go for A. So we have the weight of A, and we'll cut the strings right, the chords right here. So we have 2 times Ft taking place, and this is the FBD. I should have written that above it higher, but I didn't. And here's the X, and here's the Y, and here's the IBD of the thing, and it is accelerating upwards at 3 meters per second squared, right there, right? So this is the mass of A and the acceleration of A. So we say the sum of the forces in the y direction, mass times acceleration in the y direction, declare that being upwards right here. And I say that I have, why didn't I write it with 2 in here? Did I get the numbers wrong? Why, oh why, oh why. So I want to double check my thing right here. But this is 50 kilograms, so we'll say we have a negative 50 times 9.81 right here, right? Plus 2 times my FT, and it's going to be equal to, and it's going upwards, 50 and times 3. And I want to check out what my answer is, because on my piece of paper I didn't write down 2 times the thing. Why didn't I do that? I'm a doo-doo head, maybe? I don't know. You should be nicer to yourself. I will try to be. All right, so that's 150 right there, and we have 50 times 9.81, and those are going to add to each other, and we're going to divide by 2. I got the right number. I just didn't write the thing down. That's because my mind moves a little too sporadically. But what do we do? All right, so as I mentioned before, right, so we have the cable here, and we'll cut the cable right at here. And so the tension is the same everywhere in the cable right here. So we have a force in the cable, and we also have a velocity of that point. So we have a force and a velocity, and we could say, sometimes I go, maybe I go power. Sometimes I'll make it a paragraph symbol. Sometimes I'll go work dotted, the dot work, whatever. I say that's going to be the force of the tension times the velocity at P. And so that's 320.3 times my 6 meters per second. I get, and these are going to be newtons, and these are meters per second, so that's going to be 3,844 Newton meters per second, right? So that's newtons times meters per second, so it's a Newton meter per second. That's also a watt, right? Capital W. So it's actually, so we can even say that this is 3.844 kilowatts, maybe we could say. So now we want to write down the efficiency we know is power out over power in, but we're looking for how much power this thing takes up, right? So how much power is required from the electrical stuff. So we take the power in is going to be equal to the power out divided by the efficiency, eta, capital Eta. So we get our 3,844 divided by our 0.8, and we get 4,804 watts. So the answer is the electrical power in is going to be 4.804 kilowatts. Boom. It's good to have some type of thing to measure, kind of understand how many things are going in through. Something I should mention for homework, I think one of the problems actually now it reverses. All of a sudden the tension and the velocity are in opposite directions. So like, ooh, what happens then? Well, that makes it just like regenerative braking. Right? So now all of a sudden you get negative power, which means it's not a consumer of electricity, it's a producer of electricity. Just like regenerative brakes when you're braking in your Prius, right? You're driving along, now you press that down, it makes the motors into generators and starts to charge up the batteries. But they're still inefficient. So you don't improve the power out. You need to also reduce the amount of power output from that by way of an inefficiency you can think of. So if you watch this video, that'll help you with the homework. And that's hopefully some of our reasoning for doing it. And there's your 10-minute video.